Today we're going to be doing the specific heat of a metal. Going to try to use some items that you might have in your house. Otherwise, you can again just utilize the data that we have. I think in the lab it discusses using 4 different metals from the groups. That would be something if we were able to do it in the classroom, that we would do. But otherwise, we're going to make use of what we have. Hopefully, you have some coins or some other items, and we'll kind of get working with that. So let's get started. So not every all the materials on here are going to be working exactly the same, but we're going to do it with the best that we have. So we won't be utilizing Bunsen burner or anything like that. I'm just going to use my stove. I'm going to use a big pot of water. I'm going to be using a 7/16 socket for about a 1/4 inch wrench. That would be about 20 grams. It's a steel alloy, which for the most part I should be able to just go under the impression that it is iron. I'm going to use 5 pre-1982 pennies because they contain 97% copper, and therefore I'll be able to go with the fact that it's copper. About 5 of them is going to be about 16.5 grams. However, each penny is going to be about 3.3 grams with that. If you use a penny that is after 1983, they're about 2.5 grams, and therefore will also be much more zinc. So if you wanted to use an newer penny, if you have 5 pennies, you should be able to just go with that with zinc. I'm going to use a styrofoam cup with some water. I'm going to need a measuring cup that again has my milliliters on the other side. It's going to be important to get that 100 mil mark. Thermometers, I have a couple different ones. Meat thermometer, that will work if you have one of those. One of the thermometers from school, I'm not going to use that. Instead, I'm going to use one of the LabQuest as well. Now, you can also use other household items, such as the Allen wrench. That's about 10 grams or so, probably mainly iron. Here are some other, there's 5 nails that would be roughly around 23 grams, mainly composed of iron. These ones are zinc plated as well, or nickel plated probably as well. And so you can use a lot of different items. So use what you can, find out the composition, and go from there. So when we're heating the items, we'll want to make sure that I have my glass measuring cup, and I have the metal item inside, but it's going to be underneath the water. So as that water heats up, this glass is just going to allow that heat to go directly into the metal. We're going to have it sit there for about 10 minutes, so a lot of this is probably going to happen off screen. You can see that got my Bunsen burner, or in this case, stove, going. And we're going to just let that sit there, and I'll get some of the other items ready that will do. But for the most part, there's a lot of sitting and waiting for this lab. Now that I have my water boiling, I'm going to let that sit in there for 10 minutes and allow all that energy to transfer over into the socket. While my water is boiling, I'm taking the temperature and measured out 100 milliliters of water into my styrofoam cup to get my initial temperature of the water. Right after you put the socket in, make sure you make those measurements, keep it an eye on there, and then start your 10 minutes on your next item so that it's not taking super long. It kind of builds a little bit of the, decreases a little bit of the time waited. So I have an initial temperature of the socket, which was about 100 degrees because it was in the boiling water. And actually, if I did make the measurement, and it was really close to 100 degrees. The final temperature of the socket is the same as the final temperature of the water because it's in the same container. The initial temperature of the water is there. Now, I don't know what the specific heat of that socket is. That's what I'm going to calculate. I'll show you that at the end. All right, now that I have my last bit in there, I got my temperature, which will then allow me to have the last of my data that I need so that I can then calculate the specific heat of my items. Now that I have my calculations set up with my data that I had collected earlier, I can then find that the amount of the Q of the water of the socket, the amount of energy that was gained was 627.6 joules. Can also then calculate that the amount of energy that the water gained from the copper pennies was about 460.24 joules. Now, that amount of energy that was gained by the water was ultimately lost by the metal. And with that, you can utilize the information that you have to say that it was a negative 627.6 joules of energy and a negative 460.24 joules lost by the copper or the pennies. Now, from that information, you should be able to then calculate the specific heat of the socket to be about 0.39 joules per gram degrees Celsius. And for that of copper, to be 0.34 joules per gram degrees Celsius. And again, the pennies where we were going with the fact that they were mainly copper and that the socket was mainly iron. So that is what you'll do. You will still need to find out what the specific heat, what the accepted value for iron is to find out the percent error. Or if you did this at home, maybe you used nickel or even though a nickel is mainly copper, but if you use like a toenail clipper, a lot of those are mainly nickel, and so you could be able to use a lot of different other ones. But if you use my data, you will need to find the percent error of this utilizing these and then finding the accepted values for both iron and copper. As you did today's lab, you will find that there's probably some errors involved. What those errors actually are, it depends on how you did the lab. If you did the lab based on the video that I saw and made, it's going to be a little bit different. Some of the values might not be perfect because again, we're using alloys. In the classroom lab, it's probably going to be a lot easier to do because we will actually have cylinders that will be more of a pure metal, and therefore our measurements will be a little bit better to find for it. But nevertheless, still always that's the important part of analysis, of making sure that you have the right stuff, the right as best that you can. If you don't, where could the analysis made? I tried to mimic the lab as much as I could in my kitchen that we would have done in the classroom. So I'm interested to see what the percent error is that some of you come up with, and also where you think the errors were at.